Hello and welcome to Dare to Know, interviews with quality and reliability thought leaders. I'm Tim Rogers, and today I'm pleased to welcome Dr. Kishor Trivedi. Dr. Trivedi is the Hudson Chair in the Department of Electrical and Computer Engineering at Duke University in Durham, North Carolina. He's been on the Duke faculty since 1975. Dr. Trivedi has served as a principal investigator on various projects, including projects funded by DARPA, IBM, Motorola, Boeing, NASA, NIH, NSF, NATO, and JPL, and he regularly works as a consultant to industry and research laboratories. Dr. Trivedi is the co-designer of NASA's HARP, IBM's SAVE, SHARP, SPNP, Boeing's IRAP, and SREPT modeling packages. His book, Probability and Statistics with Reliability Queuing and Computer Science Applications, was originally published by Prentice Hall in 1982, and a revised second edition was published by John Wiley in 2002. Dr. Trivedi is a Life Fellow of IEEE and a Golden Core member of the IEEE Computer Society. Dr. Trivedi, welcome, and thanks so much for joining us today.
Tim, and indirectly Fred, I would like to thank you very much for giving me this opportunity to say a few words about my work and writings. You know, most of my
it's a great honor to have you with us.
Wonderful. Most of my career has been devoted to developing formalisms, efficient algorithms, and real-world applications for reliability and availability modeling. And certainly some aspects of these have been included in my earlier books. But by the end, nearing the end of my career, I wanted to craft a comprehensive collection of this. That is what gave rise to this latest book that we're talking about.
Yeah, I just want to mention that in a little more detail. This is the book titled Reliability and Availability Engineering with Andrea Bobbio that was published by Cambridge University Press in August. Can you tell us a little bit about your recent research that led to this publication?
Yes, indeed. So basically, I wanted to put the entire career's worth of work, if it is at all possible, into a comprehensive collection. And I was also fortunate to find that my old friend Andrea Bobbio, about the same age and similar career, wanted to do something similar. So we joined hands on this particular project. And besides all the latest formalism and efficient algorithms, we also wanted to put real-life case studies in the book, which is very rare because in a book format, it is very hard to deal with this.
Yes.
But we have managed. So to deal with real-life systems, the primary issue is that the models get very large, as you know. And so much of my research over the last 15, 20 years, you can say, has been on the use of what may be called multi-level or hierarchical models that avoid the largeness problem. And I've been fortunate to be able to use these in real-life systems at Cisco, Sun Microsystems, IBM, Boeing, to name a few. So based on this work, the last 3 chapters are devoted to specifically this topic of multi-level models and case studies. And I was also very fortunate to be able to involve with Boeing 787 FAA certification.
Yes.
One of the newer subsystems there is called current return network. And for that, there is a model type in Sharp, my tool, that was suitable. But it didn't work as it is. So we had to develop a new bounding algorithm that works for this real-life system. And we were able to not only solve the problem, but include this in the new book.
Very good. Very good. I wonder if you might, I don't want to give away too much that's in your book. I want our listeners to go buy your book, okay? But I wonder if you could share with us some more details about some of the case studies.
So the other case studies are from IBM. There are a couple of them. IBM Blade Center Availability Model. It is published actually in 2007 or 2008 in IBM Journal. which is quite a few people are attracted by that, including Intel and so on. So I sat down with IBM engineers in developing the availability model. But much more interesting later, IBM implemented SIP protocol, which is for voice over IP, on IBM WebSphere. And they wanted to sell this system to one of the major telco company in US. And telco company says, we need models. Architecture description is alone not enough. So I was actually in charge of that modeling project. And so I will say a few more things about that project as answer to some of your later questions. But that was a very illuminating project, and all details of that project are now in the book. So similarly, Cisco router example, Sun Microsystems example, I'm giving all the gory details as much as possible without revealing any confidential material.
Of course. Of course. You know, it's often very challenging to develop a model to represent a real world operating environment. There's a lot of assumptions that have to be made, maybe some limitations. Do you have any recommended practices for creating useful models?
Very, very good question. First, a very simple notion is that you have to sit down with either the designers or people who know the system very well and listen very carefully to these experts. And of course, they will give you a lot of information that is not necessary to develop the model. So you have to filter out and get this useful information, but that's not enough. What you have to do, in my experience, is to question them so that your model becomes much more detailed and representative of the system. So let me give you the example of the SIP on WebSphere. So the concentration was clearly on the software failures and recovery, because hardware failure and recovery was already done earlier in my IBM WebSphere, IBM Blade Center work. So it turns out that after the failure occurs in software, the recovery steps, detection and recovery steps, are not documented anywhere, and it is not known to one single person. So I had to seed questions based on my experience, and my interface engineer in IBM would then propagate those questions to various right people, and answer will come back a week later. And then I will ask another question and so on. So I discovered, you might say, the recovery architecture of the system after a software failure based on my questions. So if you want to have more discussion on this, for example, after a software failure occurs, either in the application server or SIP proxy, are there detection mechanisms?
Yes.
After a little while, the answer comes back, yes, there is a node agent that can detect, or a workload manager can detect. Then my next question is it possible that neither of them is able to detect? Again, answer comes back a week later, and yes. And then what happens? Manual detection. Okay. Next question. What is the recovery method used after a failure is detected by node agent or by workload manager? They will say, automated restart. I said, is it possible it doesn't work? Yes. Then manual restart. Is it possible if it doesn't work? Yes. Then reboot. Is it possible that doesn't work? Yes. Then fix a patch. So, and nobody provided me this information. Based on my experience, I had to ask the right questions, and it is the detail with which the system behavior that was captured in the model, that is what captured the attention of the potential buyer. And they said, yes, we bought the system based on the models.
I see. That's very interesting. You know, Dr. Trivedi, there's so much emphasis on testing in order to achieve reliability, which I think is completely wrong, completely backwards. The idea that you do, the way you ensure reliability is to just do more testing. And so I really like the idea of modeling as a way of improving the original design. Do you see a sort of a complementary strategy here that includes both modeling and testing?
Wonderful question. I don't think you have any bad questions here. So what I have been saying now is that so data-driven approach versus model-driven approach, right?
Yes.
And so what we find, particularly in reliability and availability, for very high reliability or ultra-high reliability systems or very, very high availability systems, purely data-driven approach cannot be used even after a system is available for experimentation, because the number of events that you need to collect is so large to get any reasonable confidence in the answer.
Good point.
That you need to be able to do models. But the models by themselves are lame because they need data as input parameters.
Good point,
so
yes.
To be advocated is that you use data-driven approach at the component or subsystem level, and you use the modeling approach at the system level. So you combine the two things together. And I have done that in the case of IBM SIP very clearly, but I see that more of this is going to happen in the future. You combine the two things.
Yeah, that makes good sense. Do you see any circumstances or applications that are not really suitable for modeling? I think you mentioned the importance of having enough data to be able to build a model.
Yes. So if the system architecture is not available, or nobody can give you that information, then without the system architecture, it will be hard to do models. The models that you do then will be what may be called empirical models, which may be like linear regression or ANOVA or what people are calling these days machine learning.
Right.
These are empirical models. But what I think is very useful, if you know the system architecture, how do components fit together? How do they interact? That information can be invaluable in forming a structural model, you might say, not empirical model. And such models can give you a lot more insight, I believe, and be able to find bottlenecks so that in all the cases I've done, their answer is going to be, okay, how do you improve? And you have to then tell them, this is the first thing you do to improve the system behavior. This is the second thing you do. That is you bottleneck identification, which will be extremely difficult to do just based on data.
Right. That makes sense. Dr. Trivedi, I'd like to change topics on you just a little bit and talk a little bit about your work in the area of software aging and rejuvenation. Can you explain a little bit about what software rejuvenation is and how that works? Okay,
so first, people have initially difficulty when you mention software aging. How does software age? There's no physical deterioration.
Right.
So the idea is the following, that suppose you have what is called dynamic memory allocation, which is very common. So the programs or applications will ask for memory dynamically from the operating system. And sometimes they don't return this memory after they are done with. So even when the application has finished and gone, the operating system thinks that somebody is holding that piece of memory. And as time goes on, more and more memory will be depleted or disappear, if you will. And so as time goes on, less and less memory is available to the operating system to allocate to the applications. And then the system will more likely to fail or slow down. So this is similar to what we see, say, aging in hardware, except there is no physical deterioration. System behaves as if it is aging.
Right. This probably explains why we often hear that the best solution is to power down and power back up again.
Absolutely. And so now that's a reactive method. That is, after a failure occurs, most likely we will reboot or restart. But if for a 24/7 system, you don't want bad things to happen in the first place. So preventive maintenance, as is practiced in hardware systems, where if the system has an increasing failure rate with age, then you can appropriately do a preventive maintenance before the failure occurs. And this proactive approach in the context of software aging has been called software rejuvenation. So software rejuvenation is nothing but preventive maintenance in the context of software systems.
Interesting. Very interesting. I think you also made a comment about the value of environmental diversity over design diversity to achieve software fault tolerance. Can you elaborate on that a little bit?
Yeah, much of the literature on software reliability deals with software reliability growth modeling, and that is applicable during testing and debugging phase. And it's very similar to that is used in hardware, DUN models, for example, in hardware. But the second stream deals with software fault tolerance, which was thought to be very different from hardware in the following sense, that if you have, in hardware, you use multiple copies of the identical type of system. Now, if you do that in software, it was thought that since both of them have the same bugs, if one copy fails on a certain set of workload or inputs, the second one is also going to fail. So they came up with late 70s, the notion of design diversity. So you give the same specifications to two different teams and ask them to use different algorithms, different languages, different development system. So that the two or more versions which are diverse that are produced, if one fails, the other one is less likely to fail.
Interesting.
So this kind of fault tolerance in software is the classical one, design diversity.
Right.
But what we are observing now, and in fact, IBM system that I mentioned, IBM SIP on WebSphere, really made me think very, very hard that in that system, after a software failure, restart was the common method of recovery.
Sure.
Failover to identical software copy is a common method of recovery. There is no design diversity. And so I started to think, how is this possible? Why is this not mentioned in the literature? And real designers are using this. So I found this notion of Mendel bug, which says that the whole notion of bug that we have all along in software is called Bohr bug now. So under the same workload, either failure will always occur due to these bugs, or it will not occur consistently. It's deterministic in some sense.
Interesting.
In the behavior. But now we are finding a lot of bugs which don't behave like that. That is, under the same workload, the bugs may sometimes give rise to a failure and sometimes not.
Wow.
So my reasoning then is that it is because of the environment in which the software is operating. And by environment, I mean that other resources of the operating system or other processes concurrently executing at the same time, they seem to affect whether or not under the same workload a bug will become a failure or not. And so if that is the case, then when I restart my software, I am changing the environment. When I reboot, I am changing the environment more. I fail over to an identical copy in another box, I am changing the environment. So what I am employing is environmental diversity as opposed to design diversity that has been used all along, or not used in the commercial systems, only in life-critical systems because it's an expensive solution, design diversity, whereas environmental diversity is a cheaper solution. And I find that this is going to be more and more used. And what the advantage then is that models become very similar to hardware models for software also. And furthermore, we are also using ALT and ADT techniques for estimating MTTF of software, much like they've been used for hardware.
Wow.
So I think it's coming full circle now. Software is becoming more and more like hardware in this sense.
Yeah, that actually leads me to my next question. I think most of our listeners are pretty familiar with hardware reliability issues. And of course, hardware reliability has been studied for, I don't know, perhaps hundreds of years, going back to the time of Isaac Newton, I think. But software reliability is becoming more and more important as we look at whole systems that are becoming more complex. Can you tell us a little bit more about some of the principles of hardware reliability that might apply to the world of software?
So the first, of course, is the software reliability growth models, which have evolved independently, but there have been hardware reliability growth models like DUN models and so on. So they can be applied with some variations. The software aging is where the preventive maintenance models that have been used in hardware can also be applied and are being applied with respect to software rejuvenation. And thirdly, in the context of Mendel bugs, we are now seeing that the availability models. Well, let me go back. Much of the literature on software talks about software reliability, very little on software availability, because software reliability models generally were for during the design, during the development and testing. Whereas software availability refers to during operation. And so our concentration has been on software during operation, and we are doing software availability models. And this begin to look very similar to hardware availability models. And we can combine them, software and hardware availability models, because the typical method of recovery is restart, reboot, or failover to identical copy, much like what we do in hardware. And finally, as I told you, very new, I think the first example of using ALT techniques, accelerated life testing techniques in the context of Mandelbug appeared in my paper in 2017. So I'm going to see, I hope that more and more people start using these ALT techniques from hardware in the context of software. We have used that for software aging, by the way, since 2010. But in the context of Mandelbugs, it's very, very new, and it's being done right now as we speak.
This is very encouraging. It's good to know that that we don't have to completely abandon the principles of hardware reliability in order to understand software systems.
Absolutely, and I love it that and in fact, some sense, I'm a hardware reliability engineer. So I've converted myself to a software reliability guy, and fairly successfully, I think.
I think so. Dr. Trivedi, it's been a great pleasure talking with you. Thanks so much for joining us today.
Yeah, thank you very much, Tim, and Fred, as I said, by implication, because he's the person behind this activity.
Of course. That was Dr. Kishor Trivedi, Professor of Electrical and Computer Engineering at Duke University. Dr. Trivedi's most recent book, Reliability and Availability Engineering, was published by Cambridge University Press in August 2017. This is Tim Rogers. Thanks very much for joining us.